In this video, we would like to talk about some properties of vectors. Many physical quantities are entirely specified by numerical values in suitable units. For instance, normal body temperature is about 37.5 degrees Celsius, and my mass is about 65 kilograms. These is some scalars. However, some quantities require not only a magnitude but also a direction for complete specification. Consider wind velocity 20 km per hour. Knowing the wind speed is not enough, as the direction of wind speed must also be given. Say, from the northeast, quantities that have both magnitude and direction are called vectors. For example, velocity or force. A vector may be represented geometrically by a directed line segment or an arrow whose direction represents the direction of the vector and whose length represents the magnitude. For example, the figure shows a vector from an initial point A to a terminal point B. The vector is denoted by AB or A. Specify that it should be an arrow on this symbol, and its magnitude can be represented by the absolute value of this AB vector or A vector. And also, we would like to define a term called unit vector. This is the magnitude of this kind of vector is 1 unit, and it is used to point out the direction of a vector. For example, look at this figure. It is a Cartesian coordination system, and we have a point A have coordinate 1, 1 and an initial point A to the terminal point B is its 2, 3. Consider the x direction. This vector, it have magnitude 2 minus 1. Therefore, in x direction, we have 1. For y direction, we have 2. Therefore, the vector can be represented by this notation, 1i plus 2j. Okay? By this notation, it is very convenient for us to do some operation like addition. For instance, we have two vectors like that, AB and this vector CD. For the vector AB, it is I plus 2j and CD is 3j. So, to add these two vectors up, we can put the CD vector to the arrowhead of AB. Therefore, we can create an vector C like the dotted line here. If we want to calculate the vector of vector C, we can have AB plus C, that is I plus 2j plus 3j. And also, we add them up part by part. For the unit vector I part, we can have only one I, but for the j part, we can have 2 plus 3. We have 5j. For example, consider a box. We have a force added on this box, F equals to 3I plus 2j Newton. And here we have a frictional force added on this box too. It is minus 2I Newton. The plus sign means positive x direction, and the minus sign means negative direction. The coordination system like this. So, if we want to find the net force of this force, we can have F plus F. So, we have 3I plus 2j, and we have minus 2I. Therefore, our resultant force can be like this. Now, we would like to talk about some product of this vector. We call dot product. By definition, dot product can be represented as that. Vector A dot vector B can be represented by the magnitude of A times B and times cosine theta, where theta is the angle between vector A and B. For instance, we have a unit vector I and unit vector J, and their angle between them is 90 degrees. So I dot J is equal to 1 times 1 cosine 90 degrees. So we get 0 because cosine 90 degrees is equal to 0. And also, if we want to calculate the vector I times I dot I, what we can get is 1 times 1 cosine 0. Therefore, we get 1. And also, J dot J, we can also have 1 unit. Okay? 1 unit. Consider example 2. If we have a vector A, 3I plus 4j, and vector B, by our calculation, we can have 3I dot 5j plus 4j dot 5j. Since I dot j we get 0, and also j dot j we get 1. Therefore, we can have 4 times 5, we can have 20. Example 3 shows that we have two vectors A and B, and their angle between them is 60 degrees. Therefore, by our definition A dot B, we can get 9 here. Consider some example more practical or more physical. We have our box here, and we applied a force F on it. It is about 3I plus 2j Newton. And also we have our frictional force, like previous example. Therefore, it is requested that we need to find the value of the work done of the box. By definition, work done is equal to net force F dot displacement S. Therefore, we can have 3I plus 2j minus 2I dot 10I. Therefore, calculate our net force first. We have 1 I plus 2j dot tan_j, and then we can multiply them together. We can have I dot tan_j and 2j dot tan_j Therefore, here we get 0 and here we get 20. Therefore, we get the dot product of a vector f net and displacement x is a scalar 20 joule. That's all for this video.